This dataset represents a sequence of measurements that were taken from ionic liquids. The ionic liquids were formed by taking mixtures in different proportions of two very similar ionic liquids, and the dataset includes the original pair of ionic liquids and then a sequence of proportions of these ionic liquids. So in principle, each one of these measurements should be a blend of the first and the last in this sequence. So we can use this to illustrate how a linear least squares approach can be used to analyze such a data set. For each sample, the same measurements were performed, namely a survey measurement and a fluorine 1s together with oxygen, nitrogen, carbon, sulfur and a valence band. Each measurement may have a different binding energy scale, and these were taken out by applying a charge correction to the fluorine 1s peaks, so these all align, and the same charge correction for each row taken from the fluorine 1s is applied to the other elements. Charge correction of spectra is important for a linear least squares calculation, and this is because the linear least squares calculation does not have a fitting parameter for the position. Unlike peak models that are defined in terms of synthetic components that have parameters such as full width half, maximum position and area, the linear least squares is only fitting area. So it's important that these data are all shifted in an appropriate way before an attempt is made to fit using a linear least squares procedure. These VAMAS blocks contain spectra that have been charge corrected. However, the charge correction is a offset in the binding energy scale. The actual data bins are unaltered, calibrating these data. So what we need to do is alter the data bins themselves, and we can do this using an option on the calculator property page. You can see here that this is the instruction to shift the binding energy scale, but on the calculator property page there's rebin selected VAMAS blocks. So I've selected all of these, they've all been charge corrected, and so when I apply this, a new VAMAS file is created, and we can verify that these are all still charge corrected, and they are, and you can see now there's no instruction to shift the binding energy scale, and that's because these data bins have been altered in terms of the binding energy, so they've been shifted, and this is true for all of these, and they're now in a state that we can use them within a linear least squares calculation. Since we have all of these spectra, we'd like to use them all in the linear least squares calculation, and in order to do this we will merge these data using an option on the test data property page that says merge irregular. So if I display each row as a separate tile in the left hand side, then the merge irregular will take each display tile and the data within the display tile and create a new VAMAS block and then write it into a new file. And here they are. So we now have a set of vectors, and each one of these represents data that were collected from the different ionic liquids. So we are now in a position where we can perform a linear least squares calculation, and the linear least squares calculation will be based on the pure forms for the ionic liquids. So if I display these in the active tile, then I select all the data that I would like to apply a linear least squares to. Then on the PCA property page there's a button that says generate spectra. When I press this button, a new file is created, and within the file the linear least squares solution is stored. The new file represents the output from the linear least squares calculation, and the linear least squares calculation was performed by displaying the two basis vectors representing the pure ionic liquid forms from 1 and 11, and then selecting the other ionic liquids that are combinations of these two pure forms, and then performing this calculation. So the result is a file containing the original data. It then includes another column that represents the linear least squares solution. So the linear least squares solution is an approximation to the raw data, and for the pure form, they're identical, but as we go down the list, we'll see that we get a slightly different solution. So you can see there is difference between the blue and the green spectra, and this is simply because one is a linear least squares calculation that is an approximation to the other, and the approximation is obtained by these basis functions being scaled using linear least squares calculations, so that when we overlay these, you can see that the green spectrum is formed by the combination of adding these two together, and these are the two different forms for the ionic liquid, the pure forms that were used as the basis vectors, and the entire spectrum has been fitted in this sense. So you can see here an oxygen peak where the linear least squares solution has fitted the oxygen peak very well. The motivation for performing this linear least squares was to assess the relative proportions of these two pure forms when they are mixed together, and to see how well these mixtures are represented by the original ionic liquids. And in order to assess this, well, you can see the quality of a fit in terms of the linear least squares, but we would also like to quantify the amount of these two pure forms of the ionic liquid within these mixtures. And we can do this by applying a region to these data. Now, as it stands, this will have created a region on the original data. So I'm going to delete this and just observe the oxygen peak from these components. So these two columns represent components, and when I create a region on this one, then I can then propagate to these other components. And the idea is that these components are scaled according to the least squares solution. So these are representative of the amount of one ionic liquid compared to the other. So let's call this one ionic liquid 1. And propagate again. And we're going to do the same for the other component, which represents the second ionic liquid. Now I'm going to call this one ionic liquid 2. So I'll propagate. So we now have regions on both of these columns. So we go to the report spec page, select in the custom report the region option here, and this will copy through region names into this name formula table. And then if I press the area report with these selected, then I generate a table that provides a measure of how much of one liquid versus the other are within these samples that are labeled 1 to 11. So you can see the first one is a pure form and it's 100%, and the last one is a pure form and it's 100%, and then in between we have trends that go from 100% down to 13% and corresponding variation in the other ionic liquid. So this is one way of measuring the relative proportions of these two pure forms of the ionic liquid when mixed in a range of different proportions and measured by XPS.